Hi everyone, and you're all very welcome to today's webinar on vibration design for floors and stairs. My name is Martin O'Gara, and helping me today with the questions is my colleague Tommy White. Great. So, as I say, we're here today to have a really quite an in-depth look at the MasterSeries Dynamic Analysis module and how it assists you in designing for vibration. We're going to specifically look at floors and stairs today. However, the module isn't restricted as such to that particular application. So just moving on to my next slide here. I promise there's not too much going on in the way of slides here. This is our vibration design tab, which is part of the MasterFrame Dynamic Analysis module. The MasterFrame Dynamic Analysis module also has other features such as force profile, time profile analyses and steady-state analyses. But by and large, the vibration design is one of its most powerful and commonly used features. The vibration design essentially operates to a number of different publications. The SAI P354, which is the design of floors for vibration, and also the Concrete Society CCIP 016, which is quite a similar publication produced by the Concrete Society, and we operate to the settings of both of those, and you can choose between those two different codes of practice in the software here, as you can see from the little screenshot. So today we're going to be looking at specifically a steel type structure with a composite floor, and we're going to be looking at how we set that up and the steps that are involved there. We're going to also be looking at then how we arrive at the natural frequencies and mass participations and such of that as well. And we'll go ahead then to look at the assessment of the response factors in that composite floor. Also in my little model, I've also got an attached staircase to the composite floor, so we're going to be looking at the individual response factors on it. And quite recently, a number of you would often have the question of what happens when there is a dynamic activity, someone is walking on a stair, and how can I assess the effect that might have on the floor that the stair is connected to. So we're going to look at that as well. And we're going to then delve into a few other specific things that are mentioned in the P354, such as vibration dose values and resonance build-up factors, and we'll explain what those are in a little bit more detail if you don't already know when we come to it. And finally, we're going to take a look at the two different types of analyses that we can do for vibration design, and that is the steady state and the transient analysis. And again, we'll discuss those in a little bit more detail. So let's just get straight into it. Now, I have a model here, which is a model which was taken from and adapted from a normal static analysis model. So we are in MasterFrame here. It's not a separate program, so you do set up your models in MasterFrame. And this model, as I say, is a floor taken out of a larger multi-story frame building. It is quite a separate model from the type of model that you would use for your static analysis, because it employs much more sophisticated analysis techniques for the composite decking itself. And in that, it actually does use finite element analyses for that purpose. So I mean, effectively, the steps that I went through in taking this was to take this floor, delete the rest of the structure that I didn't need. So I'm just looking at one floor. I turned off the area loading so that all the gravity area loading was taken out of the structure, because my loading is going to be applied through the deck being modeled as a finite element surface. Obviously, in the standard static analysis, we don't model finite element decks, composite decks as finite element surfaces. We simply use area loading distribution techniques to load up the structurally loaded members, and that is indeed a much more relevant application when you're just doing normal static analysis. However, for the purpose of assessing the floor vibration, we do actually need to employ or do much more sophisticated modeling of the floor plate, and as we can see here in this instance. So what we've done, aside from taking off the area loading, we've also then gone in and put on the decking, or represented the deck, the composite metal deck, with various finite element surfaces. So this here webinar does employ the use of actually three modules. It employs the use of MasterFrame, it employs the use of MasterFrame FE add-on, and it also employs the use of MasterFrame Dynamic Analysis. So we have a number of different finite element surfaces here, and quite simply those took me no more than 15-20 minutes to set up, which really is the majority of the changes that are required here is all really in setting up the finite element surfaces. So I have 7 finite element surfaces here, one for the main part of the slab. And let's just have a look here. We've got this with openings defined. We also have then the material is defined as a ribbed slab. And we can do that quickly by selecting one of our inbuilt library of metal deck profiles, which simply then dictates the basic rib dimensions in this little area here. Now you'll notice also that I've specified the properties of the concrete as being an E value of 38. You might wonder, well, that's an unusually high value of E for concrete, and that's because we are using the dynamic modulus for the concrete, and that's specifically mentioned in the SCI P354 in section 6. It talks about using this dynamic modulus of elasticity and then the equivalent G value, shear modulus value, subject to the Poisson's ratio from that, and that's set on this surface. Now the other thing to note is the rib axis of this surface is set at 90 degrees, because if I go back to my main border here on my finite element surface, every finite element surface has a local coordinate system, and the x-axis is going effectively this direction, whereas my rib axis is going at 90 degrees to that. So that's the reason why we have set that up as such. And really then I've got other surfaces, and you might say, well, why are these surfaces separate? The main reason being that their rib axis runs in a different direction, because I might want to run then my metal deck really in perpendicular to the radius, to the radial members coming around here. So what I've done in each of these basically is I've taken this finite element surface, and for convenience I've set up the local x-axis between two nodes of the surface so that this becomes the local x-axis of the surface. And then in effect, when I set up the material properties, I can just simply say that the rib axis is 0. Rather than trying to work out what the rib axis is, I've just altered the local surface x-axis of this little surface. And I've done the same for the other number of surfaces here around there. So the direction of the rib does actually follow this perpendicular to the radial direct axis of this little fan-shaped area at the end. Now, let me just consult my notes to make sure I know where I'm at here. Brilliant. So that's basically the setup of the finite element surfaces, but the other very important aspect in the setup of these finite element surfaces is that we dictate that all of these beams are what we call attached beams, and furthermore that they are bottom justified as well. So that really takes these members and justifies them to the bottoms. If we don't say that something is an attached beam, it won't actually be modeled. So if I were to take this guy out here, this would just become like a dummy line. There wouldn't actually be any member attached at that location. So we do want all those beams to be attached. And of course I've done that for the other surfaces around the other edges also. So that's the setup of the finite element surface. The other thing the SCI P354 tells us is that end releases are generally, you can ignore those. So there's no end releases on this. And that's simply because the deck is continuous to start off with. So therefore, full simply supported members don't really exist in reality to that effect. And at the level of movement that we're talking about in terms of vibrations, the assumption that it is fully fixed has been justified. Now, I've also applied the loading actually directly through the finite element surfaces as well. So just nip back in here and just to demonstrate that to you. So whereas previously you might have set up a floor like this and set up gravity area loaded panels and specified the loading there, whereas now our loading is specified. So I've got a 2.5 kilonewton live load and a 0.5 kilonewton additional dead load, bearing in mind that the self weight of the deck will be modeled, because I've actually specified the density in this area over here. Okay, so those are the main changes to the model that we've done, and I've told it a default mesh size as well. So the program does automatically mesh the structure. So we're just coming out of the editor here now. Oh, no, I'm not. Just need to exit there again. Oh, sorry. I've come all the way out and I just needed to actually remesh that. I apologize. Okay, so there I've got my finite element mesh, and it's reasonably regular. You have got areas where you've got odd shapes and more geometric constrictions, which lead to more of an unstructured mesh generation, but that is the nature of it. And of course, as I say, when we look at it in 3D, we will actually see that these members are attached beams and they're bottom justified as well. So it's just set up exactly the way we want it. So let's head on into the dynamic and have a look at the analysis of this. Now, the release of the MasterFrame Dynamic Analysis 2015 saw a major improvement or a major boost in terms of the solver engine. We introduced a state-of-the-art dynamic eigenvector value solver, which really saw the analysis times drop dramatically for structures like this, as well as reduced memory consumption. And we'll look at that. We'll actually be able to do the analysis of this live during this webinar, and it might take 40-50 seconds, but it is very, very quick for what is a very computationally expensive and intense analyses. Before we do the analyses, however, there's a number of things you really do need to pay particular attention to, and that is the mass of the structure. What I haven't done here is analyze the structure statically before I've come in here. It's not a requirement. However, it's just a good check to make sure that your frame isn't generally statically unstable. I know this frame is fine, but that's something I would recommend that you do. If this were a plain floor without the columns, we would actually have had the option to analyze it as a grillage, hence using 3 degrees of freedom per node and not 6, and that would cut down your analysis a little bit more, which is particularly helpful if it's a really, really large floor plate and you haven't introduced the columns in the modeling. But now we need to look at the mass of the structure. So the stiffness might be fine because it can statically analyze, but in dynamic analysis, mass is just as important as stiffness, and we need to ensure that the mass of the structure is included, and to what extent this mass is included as well is important. I know that all my loading in my finite element surfaces, both density and the additional dead load, were all in the D1 load group. So therefore I'm including all the D1 loads. And again, the SCI P354 talks about the including 10% of the live load. So I have chosen to do that by putting a 0.1 factor again against the L1 load group that I know I've used. And now it's also worthwhile coming across to the self-weight area and ensuring, yes, that the finite element density is in load group D1, which I know is included over here. That's fine. And also the self-weight of the members, the stick line members, if we want to call them those, are also in D1. So everything's included in the mass the way I'd like it to. So that's great. So now I'm going to crack on with the analysis. Now the analysis has two options essentially. You've got frequencies in a range or natural frequencies anything between 0 and 1000. Now for a structure like this, I definitely wouldn't recommend that you go for all the frequencies. The reason being that we've got a lot of degrees of freedom here. We can see over here about 16,000 to 17,000 total degrees of freedom, and you can square that number essentially to get you the if you like the overall matrix size or the number of elements that would be in a matrix of all if you were to solve for all the eigenvectors and values. And it's absolutely not necessary to do so because we're really not interested in natural frequencies of about 1000 hertz. In fact, we're only really interested in quite a finite range of frequencies. The reason why we're only interested in a finite range of frequencies is because we're going on to look at what happens to this structure when people are walking on it or running up and down the stairs. And now those activities only happen at certain frequencies, and we're only interested in frequencies which are close to or interact with these walking activities. And the P354 and the Concrete Society documents give us what we call Fourier series of different frequencies of people walking to create a simulated walking activity. And as such, that really dictates that frequencies, well, let's start off with a frequency of 0, but anybody that would be familiar with the SAI P354, for instance, knows that it asks you to consider walking frequencies between 1.8 and 2.2 hertz. And it actually goes up to the fourth harmonic of that as well, which is 4 times 2.2, which gives you 8.8. So therefore, anything, certainly anything above 20, you could argue, would be totally irrelevant, because the resonance occurs when a natural frequency is at or close to one of the harmonics of the primary frequency. So certainly I would be very safe by saying that I have a maximum frequency of 30, and any frequencies beyond 30 I know will have absolutely no bearing on the assessment of the vibration of the floor due to somebody walking on it. So that's anything between 0, which isn't really a real frequency, and 30 cycles per second is what the hertz actually means. Limiting the range of frequencies just to what you're interested in helps save a lot of analysis time and a lot of memory, and allows you to really get on with things a lot quicker. So let's click on the analysis button here to begin the process. And essentially this is going to fire up and kick off a little timer, and as I say, I'm expecting this to happen in about 40 or so seconds, which gives me a lovely opportunity to talk about our favourite subject in the office at the moment, which is of course the Rugby World Cup. And yes, we're very proud that Ireland's doing very well. Hopefully it will continue. And we got a little email from one of our users this morning, which maybe really tells us why Ireland are doing so well. And really, guys, how could we not do so well whenever we've got fantastic supporters like this carried about in the backs of leprechauns to add to it? So we thought that was very amusing. So that'll just fill a little bit of time while this analysis completes there. So this is continuing. As I say, I am expecting it to complete very soon. And there we go. So we've got our analysis. Now, we do need to pay attention to know whether or not we have done enough here, whether we've included enough. We know that the frequency range is fine. However, one of the questions we need to ask is the fundamental frequencies that we're interested in, the fundamental vertical movement of the floor, has it actually fallen within this range? Now, one of the really good ways that we can find that out is with the mass participation. We've got a mass participation here of 77%, which is reasonably good. I can order the modes of frequency by their mass participation values, and I can see here the ones that contain the highest Y direction mass participation, and I can see that I'm getting frequencies of 13. If I order it by frequency, I can see that and increase the scale a little bit, that I've got a frequency over here of about 8, and other areas 9, 10, and I'm pretty happy with that. I'm pretty happy that I'm getting a reasonably high mass participation. If I wasn't getting a reasonably high mass participation, that would tell me that perhaps the fundamental frequencies of this floor fall outside 30 Hertz, and I might need to increase this a little more to see what they are. Because what the actual fundamental frequency is of an area of floor does actually dictate your choice of analyses when it comes to doing the vibration design, because there are two choices. There is a steady state analysis and a transient analysis, and the steady state analysis is applicable where your fundamental frequency of your floor is within a certain factor of your walking frequency. Now I'm going to look at that in just a moment or two and discuss then why we might be happy to use the transient analysis in this floor, and perhaps in some other circumstances why we might want to look at the steady, or sorry, the not the transient analysis, but the steady state analysis, and why we might want to look at the transient analysis in other areas. So let's move across to the vibration design. And this is my vibration design case. All is grayed out until I add a vibration design case. And we can have multiple vibration design cases here. So I'm going to start off with the first basic one. I'm using SEI P354. I'm going to say this is a residential with non-critical areas, which affects the weighting factors. The damping ratio there, pay particular attention to that. That is talked about in the SEI P354 and the Concrete Society document. We're going to drop that down to 1% there, but there is some guidance on that in the publication. I am going to use steady state because I was able to determine just a moment ago that the frequencies are within the acceptable range for steady state. And again, I'm going to talk a little bit more about that when I come to talk about the transient analysis. And by default, we're set up here with the frequency range of walking. And again, the SEI P354 talks about a frequency range of walking, anything between 1.8 Hertz and 2.2 Hertz. And we're setting it up here. We want to then look at everything that happens in that range. So anybody walking from a range or frequency range of 1.2 Hertz to 2.2 Hertz, and everything else in between, what response is that going to have with the structure. Now, with my structure here, initially I always say, you know, it's probably unnecessary in the first instance to go for as many increments between that. So I'm going to go for 10 increments. So it'll be, you know, 1.8, 1.84, and so on and so forth. It'll deal with this at increments between that. So it will actually consider all these separate walking frequencies as separate analyses and give us really what the worst condition is. And I can see here that I am using a walking type frequency as opposed to staircase or any of these other ones that are dictated in the P354. And you can see the 4 standard harmonics that are given in the P354 here as well with their weighting factors and phase shifts. So essentially now I've got to decide, well, whereabouts in the structure do I want to assess my response factors? And really I just want to look at everywhere initially. So I will go for multiple nodes instead of single node. Single node will allow you to measure the response at one node, but I do want many nodes. And I'm also going to say that the response node, the node that I'm measuring the response at, that's i.e. the perception of the response node really is your node that you're measuring the perception of vibration at. And the dynamically loaded node are one and the same. So really what we're saying is if I am applying, considering the case of excitation being applied to this node, I'm also measuring the response at the same node. Because it is possible that you could apply excitation at one node and measure it at any other node or all other nodes and do it that way. But it's a good initial guess to say that the worst response is occurring at the same node that you're applying the excitation to. So to do that, I'm going to select the loaded nodes and let's window everything there. And we can see all the nodes being selected. OK to that. And now let's do the vibration design for this case. And that's done. And this table over here is where we see our output. Now, what it's giving us primarily is this R factor, which is the response factor. And what the response factor effectively is a factor of the root mean squared acceleration. We're measuring the acceleration at this node, and over a certain cycle, and we're getting the averaged, if you like, root mean squared acceleration at this point, and then that can be represented in an acceptable, or a criteria of acceptability called the response factor. Now the SEI P354 and other documents talk about acceptability criteria, and certainly for a floor of residential purposes, figures of about 8 have been used. Sometimes this will be dictated to you by your client, but there are some guidance in the codes of practice, and it also will depend on the usage of the floor. There are then other guidance for response factors for special purposes. So for example, if this were an office that was being used for special purposes, table 5.6 in the P354 would be a reduced response factor of 4. Certainly then also things like operating theatres would have an acceptable response factor of 1. So this is well outside the range of that, even for the normal 8 hertz that you might want for an office or for residential purposes. This is fairly high. So to that end, in this case, this wouldn't be an acceptable design, and then the user would be going back and looking at the potential of increasing the sizes of steel members or changing the decking, which isn't an exercise we're going to go through today, but really that's the processes of how we will arrive at a response factor. Now interestingly here, the worst response factor occurs at this node, 1216, and it occurs at a frequency of 2.08. So it didn't actually occur bang on 2.2 or 1.8, but somewhere in between. Now it's interesting when we get that sort of circumstance to know, well, I've only considered 10 steps. Is there potentially a higher response factor at some other value in between that, given that it looks like we're hitting a peak and then perhaps coming down again? And we can see what we mean by that. So if we take a note of that number 1216, I'm going to add a second case, and I'm going to say that I want to look at a single node this time, and it's 1216 was the node, and again putting the damping down to 1%. And this time we're going to look at 100 increments between 1.8 and 2.2. If I do the vibration design there, we can see that we do indeed get this peak. And let's not look at accelerations but response factors, and I can see I get a peak at 2.07 hertz now that I've got a slightly more refined number of steps, so that giving me a response factor of 17.35. If I go back to my first case, I can see that it was actually 14 or 16.4, so slightly lower. So it was worthwhile going and looking at the second case and putting in more steps. There's absolutely no reason why I couldn't put in the 100 steps here, but really just it can take, particularly for much larger applications, it can take considerably more time. We're not talking hours, but certainly it might take 5 minutes instead of 30 seconds if we go for the 10 or 100 steps instead of 10 steps. So this has really been useful in terms of getting me close, but this is a little bit more refinement in terms of saying exactly what area of that peak this occurs at. Now this is where the damping really does play a considerable effect. Actually, a really interesting thing to note here, and this is quite a new feature that we've introduced in just a few versions ago, in version 2015.09, we introduced the facility whereby for any one response factor, you could see the influencing mode shapes to that response factor. And we have something here called R weight, which is just about cropped out there. But R weight tells me the weighting factor that a particular mode shape contributed to a response factor. So this mode shape here of 8.29 effectively is the most significant mode shape contributing to this response factor of 1.26, where in fact actually not that 1.26, but I actually do need to go and select the right row, which would be about here. Yeah, and you can see that that's changed now. For that particular walking frequency of 2.072 hertz, this mode 1 at 8.29 hertz effectively contributed almost all the response, and the other mode shapes were much less significant. But effectively, this is the mode shape, and that's interesting because 8.29 is a factor, or 2.07 is a factor of 8.29, and in fact it is the fourth harmonic. So if we were to take the walking frequency of 2.07 times 4, we almost bang on at this natural frequency of this, which is why we're getting this resonance with that particular frequency there, because it does fall in the range of the harmonic of this mode shape here. So if I were to change that damping ratio to 2 and just run that again, we can see that that's smoothed out much more significantly now, and we can see that that 17 has reduced to 8.93. So the damping really does have a significant effect in terms of taking that peak of the resonance right the way down. Of course, if we had a damping percent of 0, the acceleration would be infinite, because we're resonating fully with that. So it's the damping which really curtails that peak in the way that is important. So that's a really important thing to get right in all your different applications that you're looking at. Okay, so what I want to look at now is then the possibility of looking at the staircase within this model as a separate entity almost to the floor. Now with the staircase, I'm just going to add in another vibration case. So we'll add in another case here, and this time I'm going to say that, oh, I think I've deleted it, not adding, not to worry. Right, I'll just add another case there, and we'll call it stair. Now, this isn't something that we automatically set, because it isn't, if you like, written in stone as to what these values should be. But the P354 does recommend that when you're looking at staircases that you consider a frequency range of 1.2 to 4.5. So you are expected really to put those in. Sometimes those are dictated to you. Some people would argue that a 4.5 hertz excitation is quite high, and that somebody is applying load to the staircase at 4.5 cycles per second, which is really fast. But that is something that you can is under your control. So I'm going to drop this down again to 1%, and then in this instance we're going to say response node equals loaded node again with multiple nodes, and we're going to select the nodes on the stair. Let's put this on the plan. Select all the nodes up to that point. And now let's do the vibration design. It is worthwhile noting that when you do the vibration design here, it does actually work through all the cases and not just the case you're looking at. So if you build this up and have lots and lots of different cases, you know, the vibration design time is going to increase. Interestingly, when I put that on a 3D, it does color the areas. Now, it actually looks like I wasn't expecting it to have, oh, that's because I'm in vibration case 1. Vibration case 2. Yeah, vibration case 2 doesn't have anything in this area because I didn't select this area, but it does have it on the stairs. And we can see here that our worst response factor is 39 occurring at node 230, and you can just about see that highlighted there on this graphic at the 4.5 hertz. So that is a response factor which again you might be able to determine whether that's within your acceptability criteria. Certainly the acceptability criteria for stairs can be higher, and values of 30 I know have been used and have been dictated to. So now looking at this here, if we did say, right, well, we did really want the response factor to be below 30, it's worthwhile considering before we start increasing section sizes or changing mass, whether or not we can make use of something called vibration dose values. Now, this isn't just applicable to stairs, but for any floor or stair. And what the vibration dose value actually mean, it gives you a way to assess your response or your vibration design using a slightly different factor, not the response factor, but a vibration dose value factor. And again, there is assessment criteria for vibration dose values in P354 in table 5.4. It gives you different criteria. Now, the reason why, or the only time you would consider using a vibration dose value is when the activity isn't happening all the time. What I should say is that in the steady state analysis, and everything that we've been looking at so far, we're looking at a worst case scenario of this walking activity or any degree of excitation that we're looking at happening at a continuous, uninterrupted fashion, which is really what the steady state is. So that somebody is exciting the structure all the time, and this is the type of vibrations. It operates into a steady state sinusoidal mode of response. Whereas in reality, that doesn't happen. Activities happen sporadically and over periods of time, and this is where the vibration dose value allows you to specify these things, where it gives you a period in seconds and then the number of times in that period that this activity is expected to occur. So for instance, if this stair were very infrequently used, I might say that we have a period whereby over a period of what this is 6 minutes, this stair might only be used one time. And we can see there, just by checking that box, we now have vibration dose values and a worst value of roughly 0.69. Now when we look at the table 5.4, it does give us acceptability ranges for buildings, and you get different ranges for days and night. And for a daytime use, you get two criteria: one for a low probability of adverse comment between 0.2 and 0.4, and then adverse comment possible gives you a range of 0.4 to 1.8, and then adverse comment probable 0.8 to 1.6. So it really maybe is all dependent on what's been stipulated here to what your client's happy to accept. If you're happy to live with the possibility of adverse comment and not the probable adverse comment, then you might say, well, that falls within the range that where that would be applicable, and I might be happy with that. Of course, you can play about with these to say, you need to set these up in accordance with what you think your activity and the frequency of your activity might occur in. Another item which can be quite useful in terms of, again, adjusting your response factor and vibration dose value is something called the resonance buildup factor. And that's whereby the activity, not so much the frequency of the activity, but the duration of the activity in terms of how long the activity lasts. And the reason why that's important is because when somebody starts interacting with a structure, walking on a structure, the structure doesn't immediately develop into this steady state sinusoidal type of movement. It has to build up to it. So it starts off from not moving at all, and then the sinusoidal movement builds up until it reaches this steady, constant sinusoidal movement where that's applicable. And that build up can be taken into account. So really, this is really saying, well, the activity might not have enough duration to develop the full steady state response. So therefore, let's look at how that can influence things. And there's two things here that, again, this is SEI P354. It asks you for a path length, and then we automatically calculate the velocity. So with that, you can see obviously that can be translated internally then in the software to a particular duration. So really, this is what this is for. So if we had quite a short path length over the stair of 5 meters, and we do the vibration design again, let's keep an eye on these numbers. You can see quite a significant impact on the response factor and the vibration dose value by simply saying that. So that can be quite dramatic in terms of the effect that can have. In other instances, it might not have any effect. So it's worthwhile taking that into consideration. So really both of these options here show us that the steady state response really is your worst case scenario of somebody continuously interacting with the structure, and you can mitigate against that or do something more realistic with the combination of these two options. Now, I'm just going to cover as well the situation whereby you might want to consider the walking activity on the stair, but you would want to measure the response on the floor itself. And this is where the response node equals dynamically loaded node isn't going to be of use to us. We do actually need to have different loaded nodes to the response nodes. We're applying the load in one section of the structure and measuring the response in another section. So in this example here, I might be interested in, well, if someone's running up and down that stair, the stair itself has its own acceptability criteria in terms of what's comfortable and what's not comfortable. But that activity on the stair might not be comfortable for somebody that's walking along this floor here, or somebody that's sitting at a reception desk here. So really what we're going to do there is I'm going to add another vibration case, and again drop that down to 1. We're still in steady state. Now, because the activity is happening on the stair, it is a staircase activity. So let's put that down to the 1.2 and the 4.5 range there. And again, just drop those steps down to 10. And we're on multiple nodes, and the loaded nodes are indeed the stair nodes. Now, interestingly, I haven't actually put a node in the middle of the tread. This is actually, I suppose, slightly conservative in that you're applying the load at one side of the stair. So bear in mind, all of these cases of loaded nodes happen one at a time. So we will consider the case of load being applied at this point, and then we'll measure the response at all the nodes. And then we'll consider the case of load being applied at another point, and then we'll measure the response at all the different nodes. And that's worthwhile bearing in mind, because when you're not using response node equals dynamically loaded node, then you also need to select the response area. Now let me just turn the 3D off so I can see really my underlying beams, and I'm just going to measure the response over this area, not on those nodes, just to keep it nice and clean. So that really means that if I've got 20 response nodes here, or loaded nodes, and 100 response nodes, then I've got 20 times 100 different situations to consider, and permutations of situations to consider at all these different time steps. So it's worthwhile saying that it's not really a sensible idea to say select all the nodes in the structure as response nodes and all the nodes in the structure as loaded nodes, because you end up with a lot of combinations, and a lot of the time you'll be measuring the response at one node due to excitation at another node far away from it, which is absolutely no bearing. So you use this selectively really when you're doing this type of thing. I think previous examples we gave of it is maybe where you might have a corridor outside an operating theatre. You might have a walking activity of something going up and down a corridor, but measure the response in the operating theatre. So let's run that, and now we've got our response factors here, and we're getting a response factor, a highest response factor of 4.5. And in this instance, the highest response node is this node, which we can see highlighted in red. And the loaded node, the load that the activity is being applied on, is this node here. Now, I was about to say earlier about these treads, if you really wanted to, you could put a node in the middle of the tread and therefore have them as the loaded node as well. Anywhere you want to actually measure response at as well, it's worthwhile saying, you have to have a node. So if I wanted to measure the response of the stair in the middle of the tread, then I would need to put a node in the middle of that tread in order to do so. That's quite important. So I've just got a little bit of time left to talk about the situation where you might decide to use transient analysis instead of the steady state analysis. Now looking at this structure here, I can see, yes, I'm getting quite a bit of vibration over here, but very little over in these regions. And that's because more than likely none of the mode shapes that are occurring in this area of the structure are really interacting with any of the harmonics of this. So anything 8.8 being the fourth harmonic of this top end walking frequency. So you might say, frequencies of 10 or 12 and above really would have little impact on this here. Now, in the SAI P354, in section 2 of the document, it talks about transient and steady state. And it talks really about your decision of when to use steady state and when to use transient depends on the fundamental mode shapes of the area of the floor that you're looking at. So if I were to come back here to my frequencies, and this is where it effectively takes you to do a bit of searching, but we're planning on doing some work on this for the 2015 version, whereby you can selectively select an area and get the mass participations of that area as opposed to the mass participations of the whole structure to allow you to identify the important mode shapes essentially in a part of the structure. So we can see, I could look at this here and go, well, this looks like one of the primary mode shapes for this area of the structure at 11.26. And the P354 says to us, for instance, it tells us on page 12 that if the frequency of the floor is high compared to the forcing frequency, and it says for walking activities up to a maximum range of 2.5, this corresponds to greater than 10 Hertz. So that effectively talks about the fourth harmonic of 2.5 being 10 Hertz. In my case, the fourth harmonic is 8.8. So therefore, any fundamental frequencies above that really might be best to assess it using the transient analysis rather than the steady state. Now what that effectively means is the structure here and its natural frequency is much stiffer than the actual the walking frequency, and as such the way the walking activity interacts with the structure is different. It never actually develops a steady state sinusoidal type movement, but rather it manifests in a series of high accelerations which correspond to each heel strike and then dissipate off quite rapidly. And in that instance, it's recommended that we measure the response in a slightly different way. The steady state is, if you like, a convenient way in that when we know the structure is going to operate or interact sinusoidally in a steady state fashion, then we can sum up the response, i.e. the acceleration, the root mean squared acceleration, using simple empirical rules. But when it's the transient analysis, it doesn't actually reach that steady state, so we need to do something more sophisticated. And that sophistication is this transient analysis, which actually goes into more a full time history analysis, whereby it calculates the accelerations at lots of different time increments over a set period, and then it numerically sums up the root mean squared acceleration and then is able to transfer that into a response factor. So I certainly would think that this area of the structure here is somewhere where I would like to do a transient analysis rather than a steady state analysis. Now looking at this, then I'm going to add another case 4, and I'm going to say it's a transient case. And in this case, you really do need to be conservative about the steps that you use and things like that, because the transient analysis is a full time history analysis operating at lots of different time steps over a set period, and as such then it will be actually much more computationally extensive and expensive than the steady state analyses. So the total time over which we're going to measure this acceleration is again dictated in P354 as 1 over the fundamental walking frequency. Now I've got a little bit of a if you like, a simplification to make here, because we are looking at a range of walking frequencies of 1.8 to 2.2. So we can take the average, perhaps walking frequency as 2. So 1 over 2 gives us a time period of half a second. So we're going to measure the accelerations over a time period of 0.5 of a second, which is one full cycle of the walking activity. And we're going to look at a time step of 0.01. This time step is important. If we choose too big a time step, we're not actually picking up all the accelerations at all the different points that we need to. And we could end up making an erroneous summation of the accelerations at all these different points. Now I do actually need as well to say that I want to look at response node equals dynamically loaded node. You can do it the other way, but again, if you don't do response node equals dynamically loaded node with transient analysis, and you've got different response nodes and loaded nodes, then that's going to drive the analysis time up a good deal more. So it's generally advisable to use response node equals dynamically loaded node with the transient analysis. Except for cases perhaps where you're just saying, well, I've just got a small number of loaded nodes and a small number of response nodes, or indeed where you're just looking at single nodes, then that's absolutely fine not to use this here, but not for large scale analyses. So let's do the vibration design on that. In fact, let's take the damping down to 1. And in this scenario, the vibration dose value and the resonance build-up factor doesn't have any impact. So having done that now, we have come up with a response factor. Actually, I'm in the wrong area. I was meant to be measuring this area, of course. I've got mixed up between the staircase that I was doing just a moment ago. I did say I wanted to look at this area. So let's run that again. Okay. And now I can see I've got a response factor occurring at certain locations of 9.3 Hertz, which is considerably more than the response factor that I was getting there previously. So it is worthwhile doing this here to assess. Now this might fall within my acceptability criteria, but I can see that that it is all occurring at the 2.2 Hertz as well. So I don't have to consider this full range. It does look like it's coming right to that 2.2 Hertz. But this series of heel strikes could potentially cause this type of response at this location. You might say, well, I'm not too worried about what it feels like there because there are no occupants there, or it's the edge of something, or an edge of an office where people won't actually feel the response, and I'm more interested in what goes on around these areas. So but that is up to you and your design criteria. So that really is where you might decide to use the transient analysis over the steady state analysis. And it's all about the fundamental frequency of that part of the structure and whether or not it falls beyond the range that would actually cause a steady state analysis. Then you're really looking into the transient analysis. That really concludes everything that I wanted to talk to you about today. It really just remains for me to say, ladies and gentlemen, thank you very much for your time here today. The MasterFrame Dynamic Analysis module is an add-on to the MasterFrame environment. For this type of application, what we're looking at today, the finite element module was also used. However, if it's just a skeletal structure that you're looking at, like a staircase, whereby you feel you don't need the power of the finite element shelves to model a structure, then the MasterFrame finite element isn't absolutely necessary. But certainly for composite floors, it is a must. If you're interested in a trial of any of these programs, feel free to contact us. We'd be happy to furnish you with a 30-day free trial on any of those. We're really pleased with the MasterFrame Dynamic Analysis vibration design. It's been used by many large companies for a wide variety of floors, and it is really delivering for people on a day-to-day basis and giving them exactly what they need. So yes, we'd be delighted to hear from you. For any of you that perhaps are considering purchasing it, I'm happy to answer any of the questions that you might have on it. So thank you very much and goodbye.